Now, before going to the other topics, let us have an overall look at the convective systems. Convection is of two types, forced convection and natural convection. When velocity or mass flow rate is involved, the fluid is flowing, it is called forced convection. The fluid is at rest, we call it as natural convection. Again, in this forced convection, you have two categories, laminar and turbulent. Laminar turbulent again coexists in external flow and internal flow. External flow means flow over a plate, flow across a cylinder, flow across a sphere, that is flow over the bodies, is called external flow. If the fluid is flowing within the body, like water flowing through a pipe, cold air passing through a duct, internally if it is flowing, that is called internal flow. The critical Reynolds number in case of external flow is 5 into 10 power 5, whereas in internal flow it is 2300. That means in internal flow, if the Reynolds number is more than 2300, it is turbulent. If it is less than 2300, it is laminar. Then external flow can occur over a plate, a cylinder, or a sphere. Again, for each one, you can have either a laminar or turbulent flow, or a combined laminar and turbulent flow. And you can also have the orientation of the plate, vertical, inclined, or horizontal, etc. And the flowing fluid could be air, water, oil, or liquid metal. See, different aspects of convection. Again, in the internal flow, you will have two types of flows. Cross sections you can take, circular cross section and non-circular cross section. Through these circular and non-circular cross sections, maybe air is flowing, or water is flowing, or oil is flowing, or liquid metal is flowing. Depending on that, the heat transfer will vary. Natural convection we will take up a little later after completion of forced and external convection and internal convection. So this is the fundamental aspects of convection to give an overall feeling of what is convection, what are the different non-dimensional numbers involved in convection, why boundary layer analysis is important in convection, how the conduction plays a role in convection, and what is a velocity boundary layer thickness, what is a thermal boundary layer thickness, how to determine the thickness of the velocity boundary layer and thermal boundary layer in laminar and turbulent conditions when fluid is flowing over a plate, and the non-dimensional number relationship, Nusselt number as a function of Reynolds number and Prandtl number we have seen in convection. Now the analysis of boundary layer to determine the convective heat transfer coefficient, you have to know the temperature distribution. Then only you can determine the dou T by dou Y at Y equal to 0. So you should know how the temperature is varying within the fluid. That is the analysis of thermal boundary layer. and the thermal boundary layer development will be influenced by the velocity boundary layer. So you should know how the velocity is varying within the boundary layer. So to understand the distribution of velocity and temperature within the boundary layers, you have to consider an element in the fluid flow and apply different equations like continuity, momentum, and energy. Thereby, the parameters like velocity, temperature, etc. you can determine. So our next step is to apply the continuity equation, momentum equation, and energy equation to a fluid element within the boundary layer. Thereby we will develop certain expressions and we will try to solve those equations to determine the so-called velocity distribution, boundary layer thicknesses, normal boundary layer thicknesses, etc. Now move to the continuity equation. Consider a fluid element in the boundary, a control volume. Generally speaking, the mass that is into the control volume is equal to mass that is out of the control volume, provided there is no accumulation or no depletion of mass within the control volume. Suppose you consider some mass is accumulating, then the mass balance equation can be written as rate of flow of mass into the control volume is equal to rate of flow of mass out of the control volume plus rate of change of mass of the contents of the coincident control volume. And mass flow rate into the control volume is given by the formula rho AV, where rho is density, A is the area, and V is the velocity. And mass of the fluid in the control volume is equal to density rho into volume of that control volume we have considered. Let us consider a control volume delta X, delta Y, and delta Z. So the total volume of this element is del X into del Y into del Z. The volume into density, you will get the mass. This is a simple equation. Mass entering in X direction, rho area this face area del Y del Z into velocity u. Mass entering in Y direction, rho area of cross section del X del Z into velocity in Y direction v. Mass entering in Z direction, rho area this plane del X del Y into velocity in Z direction w. So mass entering in X direction is rho u del Y del Z, and now we have to identify the mass leaving at a distance of x plus del X. that is nothing but mass entering at x plus rate of change of mass in the x direction into over a distance of del x. So that is rho u del y del z plus dou by dou x of rho u del y del z into a distance of del x. So this is the mass leaving at x plus dx. Similarly, rho v del x del z plus rate of change of rho v del x del z for unit distance dou by dou y into over a distance of del y. Like that, if you write this kind of analysis already we have done several times in the conduction heat transfer. First fundamental three-dimensional conduction equation while we are deriving, we have done it the same way. You can do here also. Mass entering in x direction plus mass entering in y direction plus mass entering in z equal to mass leaving at x plus dx, y plus dy, z plus dz plus rate of change of mass within the control volume. M at x plus dx is x plus dou by dou x of mx into del x. M at y plus dy is my plus dou by dou y of my into dy. M at z plus del z is mz plus dou by dou z of mz into delta z. So by writing mx, my, mz and dou m by dou t, dou m mass is density into volume rho del x del y del z by delta t plus m at x plus del x, that is rho u dou y dou z, this the second term, that is this term, and then m at y plus del y, that is rho v del x del z plus rate of change of rho v del x del z over a distance of del y. M at z plus del z, rho w del x del y plus dou by dou z of rho w del x del y over distance of del z. So cancelling del x del y del z in this equation, you will get this rho u del y del z, rho u del y del z, rho v del x del z, rho v del x del z, rho w del x del y gets cancelled. You will get this equation, and then cancelling del x del y del z, you will get dou rho by dou t plus dou of rho u by dou x plus dou of rho v by dou y plus dou of rho w by rho z. If density is not varying with respect to x, y, z, you can bring it outside the integration, and then you will get the equation dou rho by dou t plus dou u by dou x plus dou v by dou y plus dou w by dou z is equal to 0. This is called the continuity equation. If you generally consider steady state, the dou rho by dou t becomes 0, and in dimensional it is dou u by dou x plus dou v by dou y is equal to 0. Next, let us move to the conservation of momentum equation. We know as per Newton's second law, the net force acting on a body is equal to the rate of change of momentum, m by dt. The dv by dt is nothing but acceleration. Therefore, net force is equal to mass into acceleration. So sum of the x component forces applied to a fluid in control volume is equal to rate of change of momentum in x direction. This is the principle we apply to derive the conservation of momentum equation. The thing here is the forces act along x direction, y direction as well as z direction. So according to Newton's law, the net forces acting in x direction contribute acceleration in x direction. Therefore, sigma fx is equal to max. You can also write sigma fy equal to may, sigma fz equal to maz, where ax, ay, az are acceleration in x direction, y direction and z direction, and fx, fy, fz are forces acting in x, y and z direction respectively. So if you consider a fluid element in the boundary, it will be subjected to different forces. And what are all those forces to which it is subjected to? Number one, surface forces, and number two, body forces. And these surface forces are normal stresses, shear stresses, and pressure. The force that is arising out of normal stress or viscous shear stress or due to pressure are known as surface forces. And the forces that are accounted for, gravity, that is its own weight, and Coriolis forces, and centrifugal forces, and these forces are called body forces. Generally, body forces depends on the volume of the body, and surface forces depends on area of the body. They act along its area, and body forces act as per the volume. So by considering these forces and then summing up all the forces acting in x direction, equating it to mass into acceleration, you will get the conservation of momentum equation. Now let us consider an element like this. Same del x, del y, and vertical direction del z. The weight of this element acts vertically downwards, and we call that it as body or gravity force, which is equal to rho into del x, del y, del z into g. When this fluid element is moving in positive x direction, it is subjected to shear stress at the bottom plane, that is tau x in x direction. And the total shear force or viscous force, that is the surface force, acting at the bottom plane is tau x into del x into del z, area. That area is del x into del z. And when the fluid element is subjected to a shear at bottom face in the negative x direction, that is when the element is moving in positive x-axis, frictional force acts always opposite to its direction of motion. The shear force, when it acts in the negative x direction at the bottom plane, the shear force acts in the positive x direction at the top face. The stress we are considering at the bottom face is the tau x. So the stress at a distance of dy is taken as tau x plus rate of change of shear per unit distance dou tau x by dou y over a distance of del y. That is the total shear into area, again del x into del z. Coming to the pressure force, on any fluid element, the pressure always acts on the element and it goes into the element only. So therefore, when a fluid element is there surrounded by other particles, all these fluid particles will exert pressure force on the element surface towards it. Therefore, pressure in x direction and pressure at x plus dx both are acting on the element only. Let the pressure is P in x direction. So the force due to this pressure P is P into area del y del z. And the pressure at a distance of x plus dx is P plus dou P by dou x into del x into del y del z. Element volume is del x del y del z. I think it is clear. Now let us write the equations. The rate of change of momentum in the x direction is dou u by dou t into rho del x del y del z. That is rho del x del y del z is mass del m, and dou u by dou tau is acceleration. Mass into acceleration. Is it clear? Where the velocity u is a function of x, y, you can take z also, and time. Because I have considered only 2 dimensions, I have taken u, x, comma, y, and t. T is the time under unsteady state condition. Now the total derivative of u, du by dt, can be expressed as the sum of its partial derivatives. That is du by dt equal to dou x by dou t into dou u by dou x, dou y by dou t into dou u by dou, actually du by dx, etc. And this dou x by dou t is nothing but velocity in x direction u, dou y by dou t, velocity in y direction v, and of course dou t cancel, you will get dou u by dou t. Thus, the rate of change of momentum in x direction is rho dou x, rho del x del y del z into u dou u by dou x into v dou u by dou y plus dou u by dou t. Let del z equal to 1, that is what we have done. And the sum of external forces in the x direction, pressure force, viscous force, and body force, that is, body force here considered is only weight, the total weight is acting only in vertical direction, so the component of this body force in x direction is 0, so you need not consider. So net force is equal to pressure force plus surface force plus body force, that is pressure force P into del y del z, P plus dou P by dou x del x into del y del z, because this is acting in the negative x direction, minus is introduced, and tau x plus dou tau x by dou y del y into del z del x, this is acting in positive x direction, so plus minus tau x into del x del z, because this is also acting negative x direction, it is minus. And cancelling these terms, you will get here dou p by dou x, and here you will get dou tx by dou y. And substituting on the right hand side mass into acceleration, you will get rho dou u by dou y, u dou u by dou x plus v dou u by dou y is minus dou p by dou x plus dou tau x by dou y. And this tau x is equal to mu dou u by dou y. And that u is again a function of x comma y. Therefore, when you substitute dou tau x by dou y in terms of mu, you will get dou tau x by dou y is mu dou square u by dou x square plus dou square u by dou y square, neglecting the dou u dou x, dou u dou y products. So that is rho into u dou u by dou x plus mu into dou u by dou y is equal to minus dou p by dou x plus mu times dou square u by dou x square plus dou square u by dou y square. This is the continuity equation, momentum equation in x direction. Similarly, in y direction, you will get rho u dou v by dou x, v dou v by dou y minus dou p by dou y plus mu dou square V by dou X square plus dou square V by dou Y square plus rho G. This is nothing but the weight of the element which is acting in vertical direction. We have taken here an approximation del Z equal to 1 and considered only two-dimensional, and some of the pressure force and viscous forces are only taken into case. If you consider all the other terms, you will get in x momentum, in the x direction the momentum equation like this, in the y direction the momentum equation like this, in the z direction the momentum equation like this. These three equations are famously known as Navier-Stokes equation. And now you have one continuity equation and three momentum equations with unknowns u, v, w and p, and you can solve these four equations to get the velocity variation and the other unknown forces distribution knowledge. And this is all these equations are nonlinear, second order partial differential equation. Solution of this is a very tedious one. Even today, to get the exact solution, people are still doing research. Now let us move to the third one, energy equation. Energy entering into the control volume is equal to energy leaving plus energy accumulated in the control volume. As per the first law of thermodynamics, energy entering is equal to energy leaving. As usual, I have considered an elemental volume. Energy entering in x direction, y direction I have taken, and energy leaving in x direction and y direction. Z direction already I have neglected, because most of the times when fluid is flowing over a body, we will have the variation only in x direction and y direction. The z direction variation is negligibly small, so let us consider only two dimensions. So that means the net rate of heat transfer into the control volume by conduction is equal to heat entering in x direction by conduction minus heat leaving in x direction by conduction. Heat entering into the y direction minus heat leaving in y direction. So that ultimately will give you minus dou qx by dou x plus dou qy by dou y into dx dy dz. Similar to that what we have done earlier in the conduction equation. This can be written as dou by dou x of minus k dou t by dou x plus dou by dou y of minus k dou t by dou y into dx dy dz. That becomes k dou square t by dou x square plus k dou square t by dou y square, and on the right hand side the energy accumulated in the control volume mcp dt, that is rho into dx dy dz into cp into d capital T by d small t, where d total derivative, d capital T by d small t, and the dx dy dz gets cancelled. If you consider the work that is done due to pressure forces and the energy that is dissipated due to viscous forces, you can also consider and you can add it in the energy balancing equation. Now, temperature is a function of x, y, time. The total derivative dt can be written as dou t by dou x into dx plus dou t by dou y into dy plus dou t by dou small t into dt. We want d capital T by d small t, so by dividing this equation with dt, you will get dou t by dou x into dx by dt, here dy by dt, and this dt by dt. This dt by dt cancels. Dy by dt is v and dx by dt is velocity in x direction. So total derivative dt by dt becomes u dou t by dx plus v dou t by dou y plus dou t by dou t. So by substituting that, you can write the equation as rho cp dou t by dou small t u dou t by dou x plus v dou t by dou y equal to k dou square t by dou x square plus dou square t by dou y square plus the work due to pressure forces and the energy dissipation due to viscous effects. Very simple equation. If you neglect this pressure and viscous dissipation works, this is nothing but our conduction heat equation. Net energy leaving the element by means of conduction equal to energy accumulated in the body mCp dt by T. Very simple. This term is generally called convective term, and this term is called conduction term, and this is the pressure work term, and this is viscous dissipation term. If you consider steady flow, the dou T by dou small t becomes 0. You will get the equation in this manner. So we have seen the continuity equation, the momentum equation, and energy equation. Continuity and energy equations are singular, whereas when it comes to momentum equation, you have to consider the momentum in x direction, momentum in y direction, and momentum in z direction. So you will get 3 equations. So altogether, let us conclude the fundamentals of convection. The heat that crosses the stagnant film by conduction only be carried by the flowing fluid through convection. And by equating that conduction heat transfer to the convective heat transfer, you will get the convective heat transfer formula H is equal to minus K dou T by dou Y at Y equal to 0 by Ts minus T alpha. Since this H involves the temperature gradient at Y equal to 0, it is essential that we have to identify how the temperature is varying within the boundary layer, which is also depends on the velocity distribution, that is velocity boundary layer. So boundary layer analysis is important for understanding the convective heat transfer coefficient. And the thickness of the boundary layer, hydrodynamic boundary layer, for laminar flow is given by the formula 5x by root Rex. And for turbulent flow, it is 0.381x by Rex to the power 0.2. And Prandtl number is defined as the ratio of momentum diffusivity to thermal diffusivity given by the equation nu by alpha, which is equal to mu Cp by K. And Nusselt number is defined as heat flux by means of convection in the fluid to that of heat flux by means of conduction through the film that formed at the wall where the molecules are at rest. This will be HL by K, where K is the thermal conductivity of the surrounding fluid. And once you know delta and delta Prandtl number, we can determine the thermal boundary layer thickness by using the formula delta by delta T equal to Prandtl number to the power 1 by 3 for laminar flow and delta equal to delta T for turbulent flow. The continuity equation we have derived is dou U by dou X plus dou V by dou Y equal to 0. The momentum equation in X direction is rho times U dou U by dou X plus V dou U by dou Y equal to minus dou P by dou X plus mu times dou square U by dou X square plus dou square U by dou Y square. And the energy balance equation leads to rho Cp U dou T by dou X plus V dou T by dou Y equal to K into dou square T by dou Y square, neglecting the variation of temperature in X direction because temperature varies only in Y direction. We assume that as the fluid is flowing in X direction, the velocity temperature variation is neglected. These are 3 equations if we solve. This is one continuity, the second one momentum, and third one energy. You will get the solution for temperature as a function of Y and the solution for velocity U as a function of Y or X comma Y. So that velocity distribution and temperature distribution as a function of X comma Y will help us to assess the thermal boundary layer formation and velocity boundary layer formation. Knowing that the dou T by dou Y you can determine and find the value of convective heat transfer coefficient. Once the convective heat transfer coefficient is known, you can determine the rate of heat transfer by means of convection when a body is kept in the surrounding fluid. So this is in nutshell about the fundamentals of convection. I strongly advise the listeners to go through standard textbooks like these three, such that you will get the feeling of convection. Convection chapter is vast and unlimited. It is not possible to discuss each and every aspect of the convection through this webinar. So my request to all of you is take a standard book and go through the fundamentals of convection or all the other chapters which we are going to discuss. Thank you very much.